All right, we're going to go through this quiz and make sure we have the right answers and use it for a review. You can take notes on your quiz. You can study the quiz, and hopefully it will help you for the test. So the first one talks about the law of reflection. Remember that the law of reflection says that the angle of incidence, so if this is the object that the reflection is happening on, the angle of incidence is equal to the angle of reflection. So that is letter D. Whatever angle this comes in at, angle 1, the angle that it goes out at, angle 2, those two would be equal to each other. So angle 1 would be equal to angle 2. That is true for all types of reflection, whether it's regular reflection or diffused reflection. This angle in is always equal to the angle out. Number 2 says there's not a strong glare from the lights on this paper. The quiz is printed on because of, we talked about 2 types of reflection. We talked about normal reflection and diffused reflection. The correct answer is diffused reflection because a piece of paper is a bumpy surface. The light waves that come in parallel to the surface don't leave parallel. They go out at all different angles and in all different directions. So this is diffused reflection. If it's a flat surface like a mirror or like a calm body of water, then the light waves that come in, they go out the same way they came in, parallel in and parallel out. That is called normal or regular reflection. So you would see the image being reflected in this flat surface. You would not see the image being reflected in a diffused surface. You would see the image, but it wouldn't be you would see the object, but it wouldn't be the image of it being reflected. Refraction occurs in all types of waves. Remember that refraction happens when a wave hits a new medium, right? That medium has a different density, and that different density causes the speed to change, and this causes the light wave to be bent. All right, when a light wave hits a new medium, and I should say at an angle. All right, so when a light wave hits a new medium at an angle, that new medium has a different density. And if it has a different density, then the speed of the light wave is going to change, and that makes the light wave bend. That's what happens when refraction occurs, and that can happen with sound waves, light waves, ocean waves, any type of wave. When it hits a new medium at an angle, it'll have a different density, it'll change the speed, and it'll bend the wave. Number 4, refraction is a phenomenon that is observed when light changes speed. We just said that right here. So this refers to that part of the process right there. Number 5 says the amount that an object bends light is called the index of refraction. So how much is it bent? It's bent by what we would call the index of refraction. And to find the index of refraction, you're comparing how fast it would go in a vacuum. Remember, c is the speed of light, 3 times 10 to the 8th meters per second. The speed of light in a vacuum is 300 million meters per second. You would compare that with the velocity, which would be the actual velocity of the light wave. All right, and this v is always going to be less than c because it's traveling in a different material. So whether this is air or water or ice, right, or glass or diamonds, whatever, the v is going to be lower than the speed of light in a vacuum. Nothing travels faster than the speed of light in a vacuum. And so to find the index of refraction, you just compare those two. You take the 3 times 10 to the 8th meters per second with whatever the actual velocity is, you divide them, and you're going to get your index of refraction, which I would call the bending power of light. Number 6, when light travels from a medium that is more dense to less dense, light bends away from the normal. So if I have a light wave coming in and it's going from air to water, let's just say, all right, as it goes in from air to water, it's going to get bent towards the normal because it's going from less dense to more dense. Well, the opposite is also true. Let's say it's going from water to air. Well, in that case, it would come in at one angle and it would get bent away from the normal because it's going from more dense to less dense. So this is what the problem is asking. The problem is saying if it goes from a medium that is more dense, water is more dense than air. If it goes from more dense to less dense, then it bends towards the normal. All right, number 7. Number 7 says refraction occurs at the boundary of the two mediums. So it happens at the boundary of the two mediums. Like we just showed you in this one right here. The bending happens where the water and the air meet. Number 8, light would travel slowest in what material? It would travel slowest in the more dense material, which would be water. It travels fastest in the vacuum. It would travel a little bit slower in air, and it would travel even slower in water. Right? We have other things like plastic. It would travel even slower in plastic. Glass, it would travel even slower in glass. And diamonds, we talked about them being the most dense transparent material. It would be even slower in diamonds. All right, let's do this one. It says light traveling from water has an index of refraction of 1.33. So it is in water and has an index of refraction of 1.33. It goes into glass, which has an index of refraction of 1.56. If it enters the glass at an angle of 42 degrees, what will be the angle of refraction? So we want to know theta 2 down there. So we're going to use Snell's law to do that. Snell's law is n1 sine of theta 1 equals n2 sine of theta 2. n1 is 1.33 times the sine of 42 is going to be equal to n2, which is 1.56, times the sine of theta 2. We don't know what that is. That's what we're solving for. So on our calculator, we are going to do 1.33 times the sine of 42. That is 0.8899. So I would just round that up to 0.89. You might round it a little bit differently. That's okay. It was 1.56 times the sine of theta 2. We're still trying to get theta 2 by itself, so we're going to divide both sides by 1.56. So that goes away. 0.89 divided by 1.56 is 0.57. 7 equals the sine of theta 2, but we're not done. We need to get theta 2 by itself, so we're going to take the inverse sine of both sides, and that will get theta 2 by itself. So now we're going to go ahead and we're going to take the inverse sine of 0.57. And I get 34.7. So the angle is 34.7. So that means that this angle here is going to be 34.7, which makes sense because if it was going from less dense, which is water, to more dense, which is glass, from water to glass, that means it's going to get bent towards the normal. Therefore, the angle went down, went from 42, and now it's only 34.7. Light travels through an unknown substance with a velocity of 1.88 times 10 to the 8th meters per second. It travels from this substance into air. What is the critical angle? Well, our critical angle equation is inverse sine n2 over n1. It travels from an unknown substance and into air. So we need to find the unknown substance. We're going to do that with n equals c over v. N equals c over v is going to be 3 times 10 to the 8th over 1.88 E8. That's going to give us the unknown value. So if we do 3E8 divided by 1.88 E8, we get 1.59 is the n value. And so we're going to fill that in now. The inverse sine of n2, which is 1.0, which would be air, over n1, which is 1.59. Remember, the smaller number always goes on top, because if we have air, we know that the n value is 1. And so we have 1 and 1.59. So now we're just going to take the inverse sine of 1 divided by 1.59. And that is 38.97 degrees would be the critical angle between those two materials. That's pretty much it. We could have some problems here on the test where instead of having to solve for this, you might have to solve for one of the n values, or you might have to solve for this. It's still going to be Snell's law. You're still going to set it up the same way. You're just going to be solving for a different thing. We could make you use this and then take that n value and not put it into the critical angle equation. We could make you put it into this scenario. So it could, instead of saying that the n value of glass is 1.56, it could give you the velocity of the light wave in that material. And when you have the velocity of the light wave in that material, you can use n equals c over v, and then you can take it and put it in for that material. Or we could have you find the n value here using Snell's law and go the opposite way. We could take that n value, put it into here, and we could try to find the velocity. So all of those are options. They're all on your practice problems or review guide, so you should be good to go. I think that's it. Thank you.